So we're going to have a look at this question here on amines right now. But before we start, what we're going to do is we're going to make sure we understand why amines are bases and the sort of factors that could affect their base strength. So we're going to have a look at a simple amine and how it relates to the structure of ammonia. So here's the structure of ammonia. It's NH3 with a lone pair up there, and an amine is just where we might have swapped one or more of these hydrogens for an alkyl chain. So we've got amines on ammonia. And what is a base? So a base is a proton acceptor. And remember, in this scenario, what we mean by a proton is H+. So why could amines accept a proton? Well, it's all to do with this lone pair up here, isn't it? This lone pair here, sitting up here, is able to accept a proton. It's able to use it to form a dative covalent bond, so we can accept a proton. So amines are bases because the lone pair on where? On nitrogen is able to accept H+. So that's why we are a base. So what sort of factors will affect that ability to accept a proton? Well, it will be how easily that lone pair can be donated. So how available that lone pair is. Now, if you're talking about a primary amine, what we know from our earlier studies is that alkyl groups have an electron donating effect. The positive inductive effect of alkyl groups is going to push electron density onto the nitrogen. That means that the lone pair is more electron dense. So one alkyl group is going to push electron density onto that nitrogen, and that means that that would be a better base than ammonia with no alkyl groups, because ammonia doesn't have the positive inductive effect. Now, if we had a look at something with, say, 2 alkyl groups, then we've got 2 lots of the positive inductive effect. So that would be greater base strength than something with 1 alkyl group. And if we had 3, that would be even better, because we would have 3 alkyl groups. So it doesn't matter what the alkyl groups are, they will have a positive inductive effect on that lone pair. So that would be better than having 2. Oops, we didn't mean to put a third one there, did we? Let's get that and swap it for that. So from our let's just add another page. From our amines so far, we can see that we have our tertiary amines are going to be stronger bases than our secondary amines, which are going to be stronger bases than our primary amines, which are going to be stronger bases than ammonia, to do with the positive inductive effect of alkyl groups. Now, that is assuming that they are aliphatic amines, primary, secondary and tertiary aliphatic amines. What about aromatic amines? Now, aromatic means attached to a benzene ring. So what I'm going to do now is try to draw a benzene as if it's coming out of the plane of the page. And we're going to have a look at why we draw that circle in the middle of a benzene ring. Now, we draw that circle in the middle of a benzene ring because we're trying to show that each carbon has only been bonded to 3 other things, 2 carbons and a hydrogen. And so there is 1 electron left in a p orbital. Now, you might remember this from when you studied alkenes, and these p orbitals can overlap. Now, if these p orbitals overlap, then we're going to form a pi bond above and below the plane of the ring. And it's going to be all the way around, because unlike in an alkene, if we remember our alkene, if we had just a C and a C, then we just had 2 of these, and it did overlap, and it overlapped above and below, and that made our double bond. Here we've got p orbitals all the way around, so we're overlapping above and below, all the way around, and we're making that circle. Now when we've got a nitrogen next to that benzene ring, as we do in an aromatic amine directly attached, then the electrons in the nitrogen in the lone pair are also in a p orbital. So now our pi bond is going to extend out, all the way out, and we can look a bit like a frying pan, all the way out onto the nitrogen. And so the lone pair is not really just sitting on the nitrogen waiting to accept a proton. It's got itself and it's gone and become part of the pi bond. And we would describe that as being delocalized into the ring. So we would say the lone pair on nitrogen is delocalized, it's become spread out. Let's get rid of this for a second. It's delocalized into the pi ring. And the pi ring is this red overlap of p orbitals. That means it is less able to accept H+. So if we were to compare to ammonia, which has no delocalization, ammonia would be a stronger base than our aromatic amine, because the lone pair on the aromatic amine have become part of the delocalized pi bond, part of this red electron system up here, and they're not really there sitting there saying, I want to make a dative covalent bond. So now that we've just sort of reviewed why these different things are bases, and we've put them in some sort of order, so we know that these aromatic amines are the weakest, ammonia comes next, and then primary, secondary, tertiary, we can have a look at our actual question. So we can see what our examiner's trying to go on about. So the question is about three amines, E, F and G. So if I look at E, I can see that E is an aromatic amine, and that F, although there's benzene ring in all of these, F is just a truly aliphatic. The N is on the end of the ethyl group, so it's a primary aliphatic. But G is a bit confusing because it has got the N directly attached to the benzene ring, so it is aromatic, but it has also got an ethyl group, so it does have the positive inductive effect of an aliphatic. So it's got both. It's got some sort of push from one side and then a pull away from the other side. So it's got both things happening. So it says, explain the difference in base strength and give the order of increasing base strength. So if I was answering this question in the exam, the first thing I would say is why amines are bases. Amines are bases because the lone pair on nitrogen is able to accept H+. So why are amines bases? We now need to think about which one is strongest and which one is weakest and explain it. So if I was looking at this, something that is aromatic, the lone pair, let's just have a look at this in a different colour, the lone pair on the N is going to have become delocalized into the ring. Here, the N is only attached to an alkyl chain, so we're going to push electron density onto the N. Here we've got a push from the alkyl chain and a pull away, so we've got some adding and some taking away from the lone pair. So here we've just got taking away from the lone pair on E. In F, we've got pushing on to the lone pair only, and in G, we've got pushing onto the lone pair and pulling away. So which one is the strongest? We should be able to see from that F is the strongest base. Now, wants us to actually put it in increasing base strength. So if you read the question more carefully, you'll see that we want to put the weakest first. So E is the weakest. And then G is somewhere in the middle because it's got both the push on but the pull away, and F has just got the pull away, so F would be F has just got the pushing on, so F would be the strongest. Right, so why have we chosen that order? So why is E the weakest? So for E, we'd have to say the lone pair on nitrogen is delocalized, that's a mark by the way, into the ring. So what does that mean? That means it's less able to accept H+, less able to be a base. And then in G, we've got a positive inductive effect increasing electron density on N, but also delocalized into a ring. And then why was F the strongest? F just has the positive inductive effect which increases electron density. And this is, do remember, this is the positive inductive effect of alkyls. Increases electron density, makes lone pair more able to accept H+. So we need the positive inductive effect. You could have grouped F and G both have the positive inductive effect, E and G both have the delocalized. So there weren't exactly 6 separate things to say quite maybe where you would have thought you would have got the marks, because you're repeating yourself on positive inductive effect and you're repeating yourself on delocalized into the ring. But that is why we've come up with that order. So normally when students answer this question, they got all the marks except for the very first one. They forgot to explain why amines are bases. The second part of this exam question looks then at synthesizing amine F. So we just go back and remind ourselves which one amine F is, which is the one with an ethyl group. So amine F was the one where we had a CH2, CH2, and then the NH2. Let's just double check that. Yeah, on our benzene ring. And it wants us to do it in 3 steps, starting from methyl benzene, which looks like this. So we need to think, we want to start there with the methyl group, and we want to go 1, 2, 3, and end up with our structure over there. So how are we going to do that? So we need to think, how can we make amines? So we're going back and we're thinking about the different ways to synthesize amines. Well, this is, remember that this is actually on the end of a chain, so this is an aliphatic amine, and there are 2 ways to make an aliphatic amine. You can either make an aliphatic amine direct from a halogenoalkane. So to do that, wherever the N is, there would have been a halogen, or you can make it in a couple of steps from a halogenoalkane but through a nitrile. Now the reason that I'm going to pick the second one, which is through the nitrile, is because this structure only has 1 carbon in its substituent in its chain, and this one has 2. Now I need to add a carbon, and if I need to add a carbon, I need to use a nitrile. So if I were just to have a think about that, this is going to have to be our nitrile, which would have this kind of structure. So a CH2 and then a CN, because I can turn the CN into a CH2NH2. And a nitrile is going to have come from a halogenoalkane. So this is going to have come from something like CH2Cl. So we're going to be going like this. So how do I turn, really you can kind of just ignore the benzene, it is there as a distractor. How do I turn an alkane into a halogenoalkane? Well, that's our free radical substitution. So our product of step 1, so we need to say the intermediate structures, which I kind of already have done, but I'm going to do that a bit clearer. So step 1, I want to turn an alkane into a halogenoalkane. I'm going to use chlorine and UV light. Get marked for that. And the structure that I would produce would be this. And then in step 2, I am going to convert my halogenoalkane into a nitrile. So to do that, I'm going to use KCN in aqueous ethanol. And our product of step 2 would look like this. And then in our final step, step 3, I need to reduce that. So I'm going to use hydrogen and a nickel catalyst, and that's going to turn it into our product. So you can see where our 5 marks are coming from. We've got our reagents and conditions for step 1 and our product of step 1, our reagents and conditions for step 2 and our product of step 2, and our reagents and conditions for step 3.